There it is. Thank goodness. Not my clicker. Take my life, but not my clicker. All right.
Oh, hello there. Wait, Dr. D.
2 minutes.
Do you think he can hear us? Oh, I was just gonna ask about when did he said he was grading the how who when was he gonna grade the memes?
Memes are gonna get voted on tomorrow, so I need them by midnight tonight. You don't have your memes yet.
Oh, I sent it the moment
I,
we
I'm,
resigned.
I've been compiling them as they've been coming in. I put them in a PowerPoint with your team name so that the voters can't show any bias, right? They don't know who submitted. I've been laughing as they've been coming in so far. Everyone I've seen has been, this is the reason why I'm not voting on them, right? They're all really good so far. Like, what's today's date? 19? Oh, there's people sitting in the waiting room. Admit all. Welcome, welcome. Okay. Oh, did I freeze? No, okay, good. Weird. Sorry. Well, it's 9:45 and I'm not frozen, so let's get started. Lord, thank you for bringing us together this morning. Thank you for the promise of this weekend that is coming up. I pray that you would let everybody get a little bit of rest, but also get the things done that they need to, help them to get a good start on studying and just make sure that they get any questions answered that they have. In your name we pray. Amen. All right. So if you haven't started studying, what are you waiting for? All right, start studying. But Dr. D, we're not done with homework 5 yet. And what are you waiting for? Finish homework 5. Come on. Come on now. I know. You're all shrugging your face palm, all those things, right? Let me close this out, close that out. Good, good. Go. Good. Okay. So what we doing today, right? We're gonna recap, then we're gonna run some problems. You guys have some problems. All right, I've got that I gave you to do. We'll talk about said problems, and so it's looking a little light here, right? It's looking a little light, not just in person, right? I think this is the normal size of the crew for Fridays in class or Thursdays in class. But the online's looking a little light today. Um, this is,
Wonder why.
we're missing some peeps. That's not a good idea to miss the day that we do the problem. Okay. Recap: impedance and op amps. Okay. And Z of S. Z of S is the impedance variable, right? So the whole idea behind impedance is what? It's that we are normalizing an electrical circuit to be in terms of the impedance to the current, right? So hopefully we remember from circuits that all electrical elements provide some sort of resistance, right? Resistance is, yes, we use resistors to describe resistance, but wires themselves have some resistance in them, right? Nothing is perfect. The second law of thermodynamics ruins our lives day in and day out, right? Stealing efficiency from us and just wreaking havoc all over the place, right? And electrical systems is no different, right? As current goes through a wire, right, we lose some as we travel. The same way, right? The analogy is, right, that you know about friction factors in pipes, right? Same general principle, right? As the current, as the fluid flow goes down, right, we lose a little bit of velocity, we lose some flow rate, right? Because of head loss, right? Because of friction inside of our pipes. So all the idea of impedance is saying that there is some resistance to current, regardless of what type of element we're using. And we can characterize that by taking the Laplace transform of our elemental equations, right? Of our EL is equal to L I dot L and our IC is equal to C E dot C, right? The we can take the Laplace transform of those things, and we can rearrange them so that we have Ohm's law, right? Ohm's law tells us that the current times the resistance is equal to the voltage drop. And that's the idea of impedance. Impedance says that Z, which is the impedance, the resistance in this case, is equal to the voltage drop across that impedance divided by the amount of current that is going through. Okay. And it's a powerful tool because it allows us to simplify circuits that are otherwise pretty complex, right? And since everything's being treated as a resistance in a sense, right, we use the resistor rules to combine things, right? So if you have two of them in parallel, you can reciprocal rule. If you have two of them in series, you can add them together using just adding them, right? Using our series rule, right? Um, that's kind of impedance in a nutshell, right? We're just normalizing how we view circuits in the Laplace domain as treating everything as a resistance, right? And the resistance that a capacitor provides is 1 over Cs, right? 1 over C times S. And the resistance that an inductor supplies is L times S. Right? And the resistance that a resistor supplies is R, right? It's just the resistance. Okay. All the other rules of circuits still apply, right? We can still use KCL, we can still use KVL, we can still do all of those things. It's just that we're doing it in the Laplace domain instead of the time. Okay. Op amp. An op amp is an operational amplifier, right? And specifically, right, we have our own truths for op amps, right? On top of the electrical system truth. So for an op amp, right, as we showed in class the other day, right, if you had an op amp that had a resistor and a capacitor in series that bridges the op amp input to the output, right, you could use impedance to combine that, right, and then you just use the impedances and use that as part of your your KCL, right? So what are the op-amp truths, right? Well, an op-amp, an ideal op-amp, can pull negligible current, right? So I going into my op-amp, we call it IA typically, approximately 0. The voltage differential between my two terminals, EA minus EB or EB minus EA, is equal to 0, right? So if we were smart and we hooked up EB to ground, right, we can typically say that EA is 0. Right, that's in the time domain. So what happens if I take the Laplace transform? Well, it turns out that the Laplace transform of 0 is still 0. So it turns out. I guess technically it'd be 0 over S, right? If we wanted to get pedantic with it. Okay. So for an op amp, it's just business as usual, right? You use impedance to simplify all of your extraneous branches, right? Make a single impedance for everything that you can. And then you're just going to use KCL like we normally do, set the two currents equal to each other, and do all of your division in the Laplace space. Typically, we'll just leave it in Laplace space, but I mean, you could bring it back out if you wanted. You could bring it back out if you wanted. None of that, none of the impedance stuff, if you have to convert it back to, I won't say none of it. Most of the impedance problems, if you have to convert it back into the time domain, you're probably just going to be asked for the differential equation, not for the system response, right? So if you're just asked for the differential equation, then you don't have to do any of the crazy partial fraction stuff. But if you are asked for the system response, then then you've got to do the impedance and do the partial fraction expansion after that. Right? Impedance is just a Laplace transform in the electrical on the electrical side, right? That's all it is. There's a fancy name for doing Laplace transform. All right, you guys have any other questions? Anything you want to bring up now? No? Nothing. All right. Okay. So just in case we forgot, let's show these again. Oh, forgot to unfreeze this in the classroom. Yeah. That would have been nice. Right? Okay, cool. Everybody's looking at their computer anyway. Nobody cares. All right, so what are the exam 2 topics, right? Showed this at last class, showed again. We've got modeling, so we need to know how to do state space and state variables. We need to be able to create transfer functions, right? That's obviously going to play into what we just learned with Laplace transforms, right? Because we can do the transfer function method. We want to know how to linearize something, right? In case the off chance that you're interacting with a real world system that's non-linear, which is everything, then you want to be able to linearize it, right? Time domain response, right? So for first order systems, how do we characterize the first order system? What's standard form for first order system, right? That's another way of asking that first question. How do we draw the first order system response, right? If you were asked to draw a first order system response, how would you do it? For second order systems, what are the different root responses and what do they mean, right? So what are the 4 cases? What do they mean, right? If you got complex conjugate roots, what would that mean to you, right? What does stability look like, right? How do you determine stability? What do you need to characterize a second order system, right? So again, what is the standard form for a second order system, right? If you look at the standard form equation, then you can tell what you need to characterize that system. How would you draw a second order system response, right? And then finally, if I gave you a plot of a system response, could you pull out all the parameters, right? Just like in the homework question 15. Laplace transforms, right? So initial value and final value theorem, right? That's taking the limit of a function. Properties of Laplace transforms, right? So we need to know those. Do we really need to know them? I mean, they're on the master sheet, all three of those things, right? So all the things that are pertinent from the first three bullet points there are on the master sheet, right? Inverse Laplace transform. So we definitely want to know how to do partial fractions for that, right? That's the key point of Laplace, inverse Laplace transform. We want to be able to determine the system response using both the Laplace transform method and the transfer function method, right? Remember, the main difference here is whether or not we're using zero initial conditions. That is the major difference. And we talked about impedance last class, right? Impedance is just the specific case of the Laplace transform and how we can make it a little bit more useful in an electrical system, right? That's what it is. Is there any questions on the topics? It's going to be similar to homeworks 4 and 5, right? Like last time I told you guys, it's going to be similar to homework 1 through 3. And like in format and in the type of questions that you were asked, it was similar to homeworks 1 through 3. This one is going to be similar to homeworks 4. So yeah, we'll talk about that in a second, Pat, for sure. Like right now. All right, so for test mods for exam 2, right? So we're using test mods. I'll post a link in the announcements in LoudCloud, right? When we go to take the test, you click the link, right? And then it'll bring you to a website because that's what links do, right? It's just a shortcut to a website. So I'm told I'm not super good with this internet stuff. So you'll be prompted to enter your student ID number to access the exam. But if you don't know what your student ID number is, you've got a few days to figure it out. If you go into, well, I don't know if this is true for students, but I can get all yours from LoudCloud. I doubt that they're just handing those out from student to student. So figure out what your student ID number is. There's going to be a theory section. So Pat, this goes to your question directly, right? There's going to be a theory section. Sorry, spoiler alert. The first question is the anti-cheating question, right? So you're going to want to answer that one correctly, right? It's like a yes or no. So are you cheating? Yes or no? And then from there, you'll get a little text page that tells you, this is the theory section. This is how many points the theory section is worth. And when you click next, you'll launch into those theory questions. There's going to be a drop-down menu at the top. You can pick any question you want at any time. And you can go back and forth and do that. So if you'd rather do the problems first, you can. If you'd rather do the theory first, you can. If you want to just jump around and do random problems, you can do that too. There are little paragraphs between each section, which will be in its own page that will tell you, this is the theory section versus this is the problem section, right? The very first page you'll be brought to is essentially a welcome page, right? And by that I mean it's got links to the master sheet and the Laplace transform table on it, which will download a Word doc directly to your computer. Okay. Right, do all the theory questions in test mods and submit them in test mods as short answers. Unless you're otherwise directed, right, in the directions of the question, do all the problems by hand, turn in a PDF or a Word doc of your work. Please make sure that the document is legible, right? Don't put all of your work on one, like, don't make it a mosaic of all of your, one picture per page, please. Right. Format it as a portrait layout, not landscape. I know. I'm being unreasonable. Apologize. When you start the exam, right, the first page is an introduction page. You can download the Laplace transforms and master sheet. I went over that. And once you click start, your timer will start, right? So once you actually enter the exam proper, you'll get 2.5 hours. The timer will be on the bottom of the screen, continuously running. Yeah. Good question. Yeah. It's a good question. Let me think about it. So the question was, are you still going to have to video into the exam? I would like you to. Typically, before Zoom crashes, it will let you know that your Wi-Fi is garbage. Typically, at least in my experience. Let me think about ways to work around that. But as of right now, sign into class like you normally would, and we'll go from there. So,
I have a question, Dr. D.
yeah, Scott.
So instead of submitting those pictures of our work through LoudCloud, we submit it through TestMoz.
I don't know if TestMoz, so I'm not familiar enough with TestMoz, if TestMoz will allow you to upload pictures as the format, right, as a question answer format. Because it has text blocks there, basically, right?
Yeah.
So, oh, so yeah, you have to upload it in LoudCloud like last time. Yeah.
Oh, okay. And then when it says you have to download the Laplace transform tables in the master sheet, does that mean you want us to like use it on the computer rather than having a physical copy?
If you have a physical copy, I'm fine with that, right? Just as long as it's clear of any notes. But for those of you who may not have a physical copy, it's there, so you don't have to worry about it. Okay?
Alright.
Colin, question.
Do we have to submit the exam prior to the pictures and the portrait layout? Do we submit that prior to the 2.5 hours being ended, or time after that?
You got 30 minutes after to upload your stuff.
Okay,
Colin.
thank you.
So I would like most of all to have the phone with the work. If you can't, if you're like, I've got to choose between either the computer or my workspace, then show me your workspace. Well, I guess in this case that's not really gonna fly because you have to be on the computer, right? I would like both. If you can't make it work, we'll deal with it when the time comes. Okay. Obviously, I don't want to strain anybody's Wi-Fi and get them kicked from taking the exam because that would be not good. So if you have one printed out, as long as there's nothing written on it, there's no handwritten notes, I'm fine with you using either of the Laplace transform table that I provided in the announcements, which is the same one that came up, or so either use that or your master sheet that you have printed out, or you can, like, it was more of a, if you don't have it, like you've never printed it, you've just been using it on your computer, then it's right there. You can re-download it really quick and just have it. So the time after, right? That's the question. So is that 30 minutes from the, so it's impossible for me to know when everybody, right? So we're gonna go in general from the time that I say start. So after we do the intro stuff where I, talk to everybody about it, I make sure everybody's in, I'll say, all right, you read the front page first, and then before you click start, I'll tell everybody to click start at the same time, and then we'll time it from there. Right, so you get 30 minutes past the 2.5 hours from there, right? That's what we're gonna go with. So it'll probably be, honestly, based on last time, you'll probably have until like 12:45-ish, maybe 1 o'clock to get it in, depending on whether we start on time or a little bit late. Right? So yeah, and so if you, well, so all right, so the coming to class part. If you are normally a student who comes into class on Tuesdays, then you can, for sure, come in and take it. Unfortunately, because of the rules for cross-contamination and, contact tracing and things, I can't have people who are supposed to be Thursday students coming into in-person Tuesdays. I mean, if you got a study room, yeah, you can take it someplace. You just can't be in this classroom. Yeah, I apologize for that. I know that it's a university mandated thing, right? I can't. That's the whole reason why we have the split. Yeah. All right. Any other questions? I'm sure we'll.
Your voice is really muffled, Dr. D.
Okay. Is that better?
Yeah.
Better or worse? Or the same?
Better. I'd say better.
Okay.
So basically,
Yeah.
we're just doing the same, except we're just getting our tests from test mods.
Correct.
And okay.
Correct.
But the theory is turned into Tesmos and the problems are turned into Loud Cloud.
Correct. Yes.
Are we typing the theory?
Yes.
Okay.
I mean, it's a text box. So, I mean, I guess, I don't know how else you would enter it through your computer to a text box. Right? So, yeah, it's typing. It's typing. Practice your Mario teaches typing over the weekend. Okay. You guys ever play that? That was the typing game in my middle school. Sweet. Anyway. All right. Any other questions? No. All right. Here's the Tri-Quizard standings from last week. All right, we got the Zoom engineers, Dr. G's sanitizers, uncalibrated calipers, Wizard Lizards, Michael Scott Paper Company. In the bag, Zero Division, Doctors Without Doctorates, Life Livers, Warzone, SDCK, Yikes, the Swarm Lords, 185.31, Matilda's Pointing Compass, and Static Waffle. This week's points come down to your meme, right? So next week will be exam. Yeah. Next week will be the exam rankings, right? Will be your points. Don't let your dreams be memes, guys. Don't let your memes be dreams. I always mess it up. Anyway. All right, so that's the rankings, right? Cool. Let's watch something to recap Laplace transforms or inverse Laplace transforms.
All right, we're going to figure out the inverse Laplace of s plus 4 over s squared plus 2s minus 3. And if you notice, on the Laplace table, there's no entry that will give us this right away, right? But if you notice the denominator, s squared plus 2s minus 3, we can factor that, isn't it? So let's go ahead and factor this, and we will get s minus 1 times s plus 3, isn't it? Well, in this case right here, we can use partial fractions to break this apart. So this is going to be, let's put down the inverse Laplace. And for the first fraction, we will have this for the denominator, namely s minus 1. And then we will add it with the other Laplace, which is the other fraction. So let's put it down as the inverse Laplace. And for the second fraction, we will have s plus 3, right? And both of these are linear, so that means on the top, we must have constant. And now let's figure out what the constant is. Well, to figure out this constant, as you can see, the denominator is s minus 1. And all of my s are in red, okay? Anyway, I will come back to the original. I will cover up the same exact denominator, namely the s minus 1. And you have to ask yourself, how can we make this factor equal to 0? Well, we have to plug in s is equal to 1, isn't it? Okay? Then plugging 1 into this s and that s. But don't do it right here, right? So with that being said, you see we have 1 plus 4, which is 5. On the top, we have 5 over. On the bottom, 1 plus 3, which is 4. This is 5 and then over 4, right? And this is an s. This is the constant that we have. And now let's do the same right here. I will come back to here. I will cover this up. Well, how can I make this equal to 0? I have to have s is equal to negative 3, isn't it? Well, on the top, negative 3 plus 4 is going to be positive 1. So let's put down 1 and then over. Plugging negative 3 into here. Negative 3 minus 1 is negative 4. So we have 1 over negative 4, like that. All right? And now we figure out the constants. We can, of course, do this. I can take the constant to the front if you would like. Let's put down 5 over 4 like this first. And then look at this as 1 over s minus 1. Well, the Laplace of what will be 1 over s minus 1. We know that has to be e to the 1t. In other words, just e to the t, right? And then for this, let's go ahead and take this to the front. So we have minus 1 over 4. And then look at this as the inverse Laplace of 1 over s plus 3. Since the bottom is just linear, we just have to have e to the something again, right? This is the same as saying s minus negative 3. So we have to have e to the negative 3t, just like that. And this right here is it. So this is one of the situations that just use partial fractions, so you can break the fractions apart, and then you go ahead and do this and that. That's it.
That's it. No, that's it. So he used residue method, right? That's what he used. You can do it that way if you want, right? Or you can do it the way that we normally do it. Okay, so we got problems. We got problems. I want to say one thing first before we get into this whole thing here, right? Before we start chugging through problems. That double pendulum problem, right? I don't know if any of you guys looked at it yet. I hope you looked at it. That is a bear of a problem, man. That is a bear. And if you can do that problem, then I am pretty, I would say that you should be really happy that you can do that problem and that you would be very prepared for the exam. That problem is way too long to put on the exam now, right? It is. It would be the entire exam by itself. It's too long for the exam. There's a lot of algebra, right? So if you can do, like I said, if you can get through that one, you should be very comfortable with your algebra skills, and you should feel like you can do any other algebra that we have in front of us. Okay? But that's not the one that we're doing first, right? Because this is the first one on the sheet. And it says here that, in my notes say that Cody Wood is going to at least start the discussion on how to do this problem, right? So what is this problem? We've got this circuit and we want the current response I of t for the input voltage 0.08 delta t. So we're given initial conditions, right? And we're given L and R. So Cody, what we got? How are we doing this? Cody Wood. I see you right there. You're on the Zoom call. Everybody take your driver's license out. Take a look. Okay. Well, oh, what happened? Okay, well, it would appear that Cody Wood is MIA. So instead of skipping the problem, well, we can move to the next one. Cody Young, are you here? Seeing your camera. I'm not seeing you. All right, Cody, thank you. Would you mind doing your problem, right? Which looks, or at least starting yours, the maglev problem. Yeah, I'll stop sharing.
I mean, I'm not gonna lie, I don't really have it worked out.
There.
So
Appreciate the honesty. I appreciate you answering that. All right, so why don't we do this? Why don't you at least draw the free body diagram for this right now? All right, and then we'll take a couple minutes and we can see what we got and we'll start here. All right. We're gonna walk through it then.
okay. Okay, so for your free body diagram, you're gonna have the two bodies of your magnet and then your ball. And then, so for your ball, right, if we just want to look at that one, we have three forces working on it. You have your K force coming up from underneath. Then you have the force of gravity acting on your ball from above, as well as the force of the electromagnet that will be acting on the ball from the magnet. So those are just three of them right there. But yeah. And then going off of the magnet itself, you'll also have a FEM force on the magnet. So that's the other body system. And then
Is it the body that we're worried about there? Because that should be moving, right? So what's generating the electromagnetic force?
right, that would be the inductance of the coil around it.
Mm-hmm. And how do we describe that circuit? If that makes.
Was it LR circuit?
Yeah. Right. So it's an FBD and a circuit diagram, right? We've got some voltage in and a resistance and an inductance, right? So it's our FED and our circuit diagram, right? This is just an electromechanical system. I didn't put the weight on here, right? And the reason that we don't put the weight on here is because we have the spring there, right? And we assume that we're starting at equilibrium. And if we're starting at equilibrium, then the deflection in the spring already takes into account the weight and balances it out, right? Okay, cool. All right, so what are my inputs and outputs?
All right, so your inputs would be the your input voltage, and then your outputs would be the distance traveled by the ball. So whatever your z value is.
All right, so yeah, that's one thing we didn't put on our free body diagram, right? Was the distance. Well, we can call it z or x, whatever. I'm going to call it x. We're going to say it's positive upward, right? So yeah, my input is E in, my output is X, right? That's overall for the entire system. And what were we asked to find here, right? Overall, we wanted the positional response using the transfer function method, right? So I want to know what is the total. I want to know what is the total system response from En all the way to X. So I need the total transfer function for the entirety of the system, right? I need to go from En all the way to X. Just in case you guys were wondering, most people think that Cody Wood is playing Warzone. Is what most of them. Followed up by sleeping, and you guys are very kind, but I really do feel like he's just ignoring me at this point. That's what I would say. All right, cool. Thank you for answering. All right. So we were told that we want to use the transfer function method, right? And we weren't given any initial conditions, which is fine, because if we're finding the transfer function, we need 0 initial conditions anyway. We understand. All right. My camera going off. Yeah. This whole production is a mess. Nope, it's just really, there it is. I'm back. All right. All right, so we've got inputs and outputs. We've got our diagrams, right? So Cody, hit me with some mathematical truths here.
All right. So the big one is that we have to relate inductance to electromagnetic force.
Mhm.
And let's see. This is where my notes being a mess is an issue. Well, we obviously have our forces of motion on the ball diagram.
Sure.
So we have our some of the forces equal to mx double dot, and f of k is equal to kx.
Mhm. Absolutely.
Sorry, I'm trying to.
What about the circuit? What do we got for the circuit?
I'm trying to find my notes.
Yes, Pat. You would need Ohm's law. Right, and the one thing that we didn't draw here, right, is our current. We should definitely draw that. Right, and yeah, L. What else do we need, right? This is a single branch circuit, right? There's no nodes, so there's only one Kirchhoff law that we can apply here, right? Which is obviously the voltage law, right? Because we only apply the current law if we have a node. So we've got KVL here, and our KVL tells us that En is equal to ER plus EL. There is the one other truth that Cody was talking about though, right? Which was, how do we relate this electromagnetic force, right? How do we couple these two systems, right? What is the equation for electromagnetic force? And I'm pretty sure that's on the master sheet, right? And it might be written as the general form with the cross product in the electromagnetism section. Right? So what do we got? What's FEM? Anybody? I'll open it up to anyone. Cody, you can be off the hot seat for now. Thank you for participating in that. Appreciate it. So what's FEM? How do we find it? Anybody? Use the chat. Yell it out loud. Tweet me. You can put it in Discord. Right? You can send me an email. Any of those. Anybody. What's FEM?
Force of magnetic field is IL cross product of B.
Yes. It's I. Is it I sub L or I script L?
I script L.
Right. And script L is the length of the wire, and B is the electromagnetic density, right? How strong my field is. And I is obviously the current, right? So it's B cross L times I, okay? But if we have fields that are perpendicular to one another, like this one, right? My field line is coming from the electromagnet. Hold on. Well, I can't go back. PowerPoint won't let me. But if we have something that's parallel to the, or perpendicular to the field lines, this becomes B times L times I sub L. Okay? That's what the electromagnetic force is, right? So electromagnetic force depends on how strong my field is, how much wire I have, and how much current I'm pumping through. In this system and in general, we assume that B and L are constant, right? I have some, my electromagnet, I have some length of wire, right? That is a constant. I'm not changing that as a function of time. B is a function of your ferromagnetic source, right? Right? It's a function of the metal that you're using to create this electromagnet. I is the only thing here that's changing the time. So B and L are constants. Also, B and L are not given in our problem statement, right? We weren't given B and L. So we're gonna have to carry B and L through the entire thing. Right? We're gonna have to carry B and L through the entire thing. But this is it, right? This is everything that we need at this point to start our reduction. Right? So that's everything we need to start our reduction, right? So we can do that here. Just trying to get rid of that for sure. So reduce. All right, we'll start with the electrical system, right? So I've got E in, right? So I'm starting with my KVL, right? And I'm just gonna plug things in, right? Because EN was equal to ER plus EL. So this is just gonna be L I dot L plus R I sub L. That's what we're working with. Okay. Before we move on, that's the whole model for the electrical system. Now, we've seen this one a lot. RL circuits come up a lot in the stuff that we do. Okay. So what do I do with this, right? I need to do the transfer function method. So at some point, I'm going to have to take a Laplace transform. I might as well just do it right. Now, if I take a Laplace transform of this, and remember, we're eventually going to make a transfer function. So we're using 0 for all of our initial conditions. This will become what? Well, it's going to be capital E in of S is equal to LS IL of S plus R IL of S. And I'll rewrite it when I group my like terms. All right, we've got laser times IL of S. We're gonna leave that for a second, right? I'll call that equation 1. Call that equation 1. So then we can focus on the mechanical system, right? We have sum of our forces is equal to mx double dot, right? So I've got FEM, which is B times L times I sub L. And I've got negative Kx, right? Because my spring force was pointed the opposite way. Is everybody cool with the mechanical model? Yeah. No, that's okay. You just have to ask. I can run through it the longer way.
I forget why. Why do we get an S for an L but not for an R again? Is that because of the independences?
Sorry, Carl. Say that one more time. You're cutting out a little bit.
Oh, sorry, it might be just the Wi-Fi. Why do we get an S for the L for like L but not R when we Laplace everything?
So I didn't mean to erase that. Because of the I dot term, right?
Oh, yeah. Okay, never mind.
So just remember, for anybody who's wondering, right? In general, right? If we take the Laplace transform of the derivative of a function, the first derivative of a function, we get S times Y of S minus Y of 0, right? Minus the initial condition. When we have 0 initial conditions, right? This term goes away. And that's why we end up with Sy of S. If we had d, like the second derivative of this, right? This would be S squared minus Sy of 0 minus Y dot of 0, right? But again, our initial conditions here are 0. So we just end up with this. So, right, whenever we have 0 initial conditions, taking the Laplace transform of our equation, when we have derivatives in there, it becomes just an S squared for all of an S for all of my dots, right? One S per dot. Okay. So if I Laplace this and I rearrange at the same time, right, I'll get ms squared plus k times x of s is equal to b times l, which are both constants, times il of s. Well, yeah, this right here, sure. So yeah, I can go over that, right? So this would be mx double dot plus kx is equal to bl I sub l, right? Remember, this is a function of time at this point. I have to, with my handwriting, you don't want me using lowercase I. It's not gonna be pretty for anybody. Right, so then if I take the Laplace transform of this, right, I'll end up with ms squared times x of s plus k times x of s is equal to b times l, which are both constants, times il of s, right? And then all I did was I regrouped my x of s terms, right? That's all I did. Which brings us to this right here, right? Which I call equation 2. Right, and that's all we needed, right? Normally, if we were to do this problem, like if this was a first exam problem, right, you get the model, you get the 2 equations, and we're done, right? The third order system, we're good. Okay. But we're asked to do a little bit more here, right? So we're gonna have to create our transfer function, right? And the transfer function that we want, right, we were specifically asked for what? We were specifically asked for the positional response, right? So we want x of t. That's what we're trying to find. And if we want x of t, we need the transfer function x of s over e in of s. This is the transfer function we're trying to build. So I need one equation that is completely a function of e in and x of s, right? So how am I going to do that, right? How am I going to do that? I've got to solve these I have to solve one for IL of S, and I have to plug it into the other one, right? So the way, it doesn't matter which one you solve for which, right? So I'm going to solve equation 2 for IL of S, right? So I'm going to take this, solve for IL of S, right? And if I do that, I get IL of S is equal to MS, oh man, that was a mistake. MS squared plus K times X of S divided by B times L. Right? So what I did was I took that equation 2, I rearranged it, I solved for IL of S, right? Because the whole point of this is I'm going to take this expression for ILS and I'm going to plug it into my equation 1 up here, right? And if I do that, I'll have everything in terms of E in and X of S. That's what I'll have. Okay. So far, so good. Everybody tracking. Right? The only thing different than what we would do from the model so far is that we had to apply a Laplace transform with a 0 initial condition. That's the difference. So we're going to combine these two things together, and we're going to make one overarching equation for the entire system that bridges both the electrical side and the mechanical side. So I'll take this ILS equation and I'll plug it in. Yeah, AJ, what's up? Mhm. Right, so if you were just asked for the model, right, you would stop at giving me the two equations for the model, right? One for each side. But this specifically says we want the positional response, right? And so positional response with a transfer function method, right? And because we've seen that, we know, first of all, that we're going to need a transfer function, right? Because it's in the name. So which transfer function do we need? Well, our output here is going to be X of S, right? And our input for the entire system is E in of S. So this is the transfer function that we're trying to make. Because when we take the Laplace transform of this, or the inverse Laplace transform, right, we'll get X of t over E n of t, right? Yes. The output. Remember, transfer function is the ratio of your output to your input, right? That's what it is. We can have multiple transfer functions, right? In a system. And this system has two subsystems, right? It's got the electrical subsystem, which would have its own dynamics, and it's got the mechanical subsystem that also has its own dynamics. But we want to know the overall dynamics of the entire system combined. So we want to use our global input and output, right? This is a single input, single output system, right? I give it some voltage, I get some positional difference. That's what we get. Okay? This is what we're trying to do. Okay? Good question. Any other questions? All right. So we'll take that IL of S equation, and we'll plug it into our En of S equation, right? So we have En of S, right? Our original equation told us that En of S was equal to Ls plus R times IL of S, right? That was equation 1 that we came up with. And we're going to plug, instead of IL of S, we're going to plug in our other equation, right? Ms squared plus K times x of s over b times L. Which really, I mean, this is the denominator for the whole thing, right? That's cool. Cool, cool. All right, so far we've just done a little bit of algebra, but hey, this is the nice thing, right? Now we have one equation that describes the global input to the global output, right? And so I can form my transfer function now, right? I want x of s over E in of s. And how do I do that? Well, I have to divide out by all of this, right? So all this is going to go over here, and this is going to come over. Let me use a different color, right? This is going to come over here. And that looks like a mess on the screen, right? For sure. But remember, I'm just solving for this, right? So let's do it one step at a time. Let's do it one step at a time just so it's clear what we're actually doing. Get rid of all that. I'll rewrite it. Laser from Mrs. K over blah. Right? So I'm gonna bring this over, right? I'm gonna bring this part over. We'll do this to the red. We'll do the red part first. So I'm gonna end up with, well, if I divide by LS plus R over MS, right? If I divide by that, isn't that the same as multiplying by the inverse of it? Right, I'm just gonna flip it over. So it's gonna be B times L over laser plus Ms. K. I don't know why I wrote E in S. It's E in of S for sure. Right, and that's equal to X of S, right? And take note of that because that's going to be important in a minute. But first thing we need to do is get the transfer function, right? So to get the transfer function, X of S divided by E in of S is just equal to B times L over LS plus R times MS squared plus. There we have it, right? And if we wanted, we could plug some numbers in now. Now would be a good time to plug in some numbers, right? Because I've got values for L, R, M, and K. So why don't I plug those in? So B times L over 0.5 S plus R. R was given as 100 kiloohms. So do we just throw kiloohms in here or what? How does this affect our, well, when you use base units, right? So 100,000 ohms. Times S squared plus 4. Right? So all I did was plug in my values for M, MK, L, and R. Right? That's all I did. And that kind of looks like a transfer function, right? I mean, sometimes we would expand that, but we're not going to expand this, right? Because we know that if we need to do a partial fraction expansion, we're going to want it factored for us already, right? So this is really nice for us. This is really nice for us. There's one piece missing though before we start doing our before we start looking at the analysis part of it, right? And that is that we need to know what E in is, right? I'm looking at the wrong column. So E in, right? What is that voltage? That voltage in was given, right? We were told that E in of T was equal to 5T. That's what we were told. But if we're going to analyze this right? Because we can solve this, right, for x of s is equal to b times L over, well, let's use the numbers right now, right? Over 0.5 s plus 100,000 times s squared plus 4 times E in of s, right? Because I want x of t. So if I want x of t, I have to solve for x of s. But in order to do that, I need to know what the Laplace transform of my input is, right? So what is the Laplace transform of 5t? Well, we can run to our tables, right? Well, we know that a constant's going to get pulled out because that's how it all works. So in a Laplace transform table, what's the Laplace transform of t?
S.
S? AJ got it. It's 1 over s squared. Laplace transform of t, if you go to the table, right, is going to be 1 over s squared. Okay, that's what we're looking at. Okay, so now we have everything. Now we have everything that we need. Hopefully, we still have a slide left here. Let's. I'm gonna double check real quick while you guys finish right now. We do. We're in business. So while you guys are finishing up copying that down, I'm just gonna rewrite my equation up here with my Laplace transform input in it. Okay. And I know it's not shared on the internet right now, but I'll unfreeze it in a second, I promise. Oh, that was weird. Nope, no, it's not. So if I plug my numbers in and put in my input, I'll get this. Right, so all I did was I took the Laplace transform of my input function and then I multiplied it by my transfer function, right? And now we have everything that we need to solve this, to write our partial fraction extension. Except for my calculator. I don't need that. Now let's do this. So where we go from here, right? Well, we've got a Laplace transform for x of s. We're going to check the roots of the denominator and check what the poles are. Right? So let's check the poles. Well, it turns out S1 and S2 are equal to 0, right? S squared is going to give me a repeated root at 0. How did he do it? How does he find it? Good. We get a repeated root at 0, right? S squared is equal to 0. You take the square root of 0, it's 0. There has to be 2 roots because it's squared, right? So it's 0. 2 zeros. What about the next root, right? S3. Well, S3 is going to be equal to negative 200,000. And S4 sorry, S4 and 5 is equal to plus or minus 2j. So this has got something for everyone, right? It almost hits all four root cases. It's got repeated roots, it's got a distinct real root, and it's got imaginary roots, right? So we're running the gamut here. We're running the gamut. But this is good, right? Because we know what we're basically going to expect here, right? Roots of 0 are going to give us this straight line behavior, right? We know that from when we talked about roots. Distinct real root that's negative is going to give us a sinusoidal decay. And a completely imaginary root is going to give us a harmonic oscillation. Right? It's going to give us a sine wave. Not a damped sine wave, a pure sine and cosine. Pure sine and cosine. That's what it's going to give us. And we know that, and because we know that, we can write our partial fraction expansion. That's going to tell us that we have a over s squared plus b over s, right? Because that's the rule for repeated roots, right? We'll have 1s something over s squared plus something over s. If I had a cubed root, it'd be something over s cubed, something over s squared, something over s, right? We got to account for all these things. Plus c over 0.5s plus 100,000 plus ds plus e divided by s squared plus 2. ds plus e. Why do I have ds plus e there? Because there's two roots associated with the harmonic oscillation, so I have to have a constant for each of them. Sorry, it's s squared plus 4 plus 2 squared. 2 squared. I forgot the square. Don't forget the square. It's important. Right? Correct. We'll get to that point in a second, okay? Because once we multiply through by the denominator, this is going to make another thing. So as squared plus b, a over s squared plus b over s plus c over 0.5 s plus 100,000 plus ds plus e over s squared plus 2 squared is all equal to 5bl over s squared, right? So these two things are equal, right? Those two things are equal. So ds plus e, because I know that I have a harmonic oscillation, I don't know how much of it is sine and I don't know how much of it is cosine. There's two roots though, right? Because it's plus or minus. So I need ds plus e, right? Think of it this way. Because I know it's a harmonic oscillation, but I don't know the composition of whether it's a pure sine wave or a pure cosine, I'm going to use both to make it. And the math will play out whether, tell me which one is bigger or if one is 0. Right, how would you, because that's basically the rule for cosines and sines, right? So this is why you always check the root response, right? Because we're gonna use our root responses to guide how we form our Laplace transform, or how we form our inverse Laplace transform. You have to do it. You have to do it together. Typically, it's done together, and then we'll end up doing a second round of partial fractions on this to figure exactly which part of it is sine and which part of it is cosine. You'll see. So I would recommend, you don't have to, right? But if you take it to the next step further, it becomes a little bit more complicated up front. Right? So if you start it like this, you'll definitely at least be pointed on the right path. Okay? Okay, let's see what I'm talking about. All right, so I'm gonna multiply all of this by s squared times 0.5s plus 100,000 times s squared plus 4, right? And I'm gonna do the same down here. Not s squared plus. All right, so I'm gonna multiply both by this, right? And if I do that, the denominator on the top portion there just becomes this, right? It cancels out. I get 5BL is equal to, and this is where it gets really fun, 0.5 AS cubed plus 100,000 S squared plus 2AS plus 400,000 A plus, now we can do our B terms, 0.5 B S to the fourth, right? So, okay, so this first one, A over S squared, right? The S squareds cancel, I'm left with everything else. And I've just multiplied through here. That's all I've done, right? For B over S, only one of the S's cancel, right? Only one of the S's cancel. So it's going to look a lot like the A portion, but there's going to be an extra S term floating around, right? C over 0.5S plus 100,000. Well, all I'm left with is S squared times S squared plus 4, right? And so this is going to give me CS to the 4 plus 4 CS squared plus 0.5. Oh, right, so that's what I'm left with there, right? So C times 0.5 S, oh, sorry, C times S to the 4, right? C times S squared times S to the 4. S to the squared is S to the 4th. S squared times 4 is S to the 4. S squared, so I get C, 4C S squared. Now the next part, right, gets rid of that S squared plus 4, and I'm just doing the rest of it here. So I'll end up with 0.5 D fourth plus 100,000 DS cubed. And so these are long. 0.5 E S cubed plus 100,000 E S. Right. Questions, comments, concerns? What's that? How did I do it? Mostly magic. Patience and time. Patience and time. So all you do, right? So let's kind of walk through it a little bit piece by piece, right? So A over S squared times this whole long nasty S squared times, right, all that. The S squareds cancel, right? So this is just A times 0.5 times S, right? And so this whole first part just comes from this. A times 0.5 S plus 100,000 times S squared plus 4, right? Because the S squared cancels, right? Because originally this was over S squared and this whole thing was times S squared, right? So those two go away. And we're left with that. And then when you expand this out, this is what you end up with right here, right? Yeah, exactly. And you do that over and over again, right? And just rinse and repeat. And just rinse and repeat. What's that? Sorry to hear. Potentially something like this, yeah. I mean, so honestly, these problems are like they take a little bit longer, right? This one's a third order system. Third order system is going to take longer than a second order is going to take longer than a fourth, right? But it's just the same process, just rinse and repeat every time, right? And this actually became a fifth order, right? Because of the input that was given. Okay. That's where that comes from, right? So we got to solve this. So we've got to solve this. So we're going to regroup everything based off of our coefficients of our s cubes, s squareds, s to the first, and s to the zeros, right? So in this case, my highest order s term is s to the fourth, right? So let's start there. Please, please start there. Nope, not intermission yet, guys. Apologize. Give me a sec. Underestimated the number of slides. Question was, are there going to be multiple like smaller problems or just like one big chunky problem? Yes. Yes. So, I mean, it's going to be similar to what you guys had in the homework. That's the best I can give you, right? So, similar to these, right? You're not going to, so remember, you get 2.5 hours. Right? And if it took me longer than 30 minutes, then, you know, it's outside the bounds of doing amazing. Right? Something like that, sixth order system, the double pendulum, that's way too long. A third order system is probably pushing the limits of what you can comfortably do on an engine. So this is a fifth order system. All right. So our highest order term in this equation is s to the fourth. Well, that's 0 on the left because there's no s to the fourth terms on the left. My only s to the fourth terms here are 0.5b plus c plus 0.5d. My s cubed terms, 0 equals 0.5 times a plus 100,000 times b plus 100,000 times d plus 0.5 times e. We've got an s squared term. 0 is equal to 100, not 10, but 100. 100,000 a plus 2b plus 4c plus 100,000, excuse me, e. S to the first, 0 is equal to 2a plus 400,000 b. 1,000 and s to the 0. And finally, we got something in here. S to the 0 is 5b times L is equal to 400,000 A. So I can solve this one immediately, right? BL over 80,000. And I can take this one right up to here immediately. I can solve for B, right? Because B is going to be 2. And so it's going to be negative, well, 2 over 80,000 is going to be negative BL over 40,000, right? And then the rest of them, well, I've got to solve a system of equations, right? So I got to plug A and B into those and solve a system of equations. Oh, sorry, I forgot something. No, that's not what B is, right? B is equal to negative 2A, which is divided by 400,000, right? So this is negative B over L over 40,000 times 1 over 400,000, right? So it's like a really small number. So B is actually negative B over L. What is that, 16 million? Let's just call this, instead of doing it that way, let's call this 6.25. No, wrong one. This was 1 over, was it 40 or 80? That was 80. Over 80. BL over 80. Okay. BL over 80. And B is 6.25 times 10 to the negative 11 times BL. This is a super high resistance. Right? Then we got to take both of these, plug them into the other 3 equations, and solve the system of equations, right? So let's do that. The reason I'm doing it on my calculator right now is because that's a great question. Why are you doing this on the calculator right now, Dr. D? Well, see, the problem here is that Dr. D did it in his notes with the wrong input than the one that we did in class here, right? I did it with 1 times t squared instead, or 1 times t instead of 5 times t. And that doesn't just change it by 5 times, right? So you have to do the math out. So give me 1 sec and we'll run it through. You guys can also solve it if you like. Make sure I put these in right. Yep. So if you do this, right, you get C is equal to 0. D is equal to negative 6.25 times 10 to the negative 11. And E, here, let me use the capital letters since that's what we're using. C, D, and E is negative BL over 80,000. And also, this is times BL, right? That's times BL. So yeah, gross, right? Gross. So that's what we get. Well, C being 0 is actually pretty nice, right? Because then we just end up not getting something for that response. Okay? That's part that we can ignore.
Dr. D, real quick.
Yes.
Why would there be a BL in front of the E?
It's not in front of the E, Scott.
Oh, that's for the D. Sorry.
It's okay.
Okay.
There you go. Sorry, yeah, I realized it was really close when I wrote it. Batting 1,000 with handwriting, as usual. As usual. Okay. So what do we do with this now, right? Well, remember, x of s was equal to a over s squared plus b over s plus c over, s plus something plus d s plus e, right? So I can plug these things in and my x of s expression now. So I've got b l over 80,000 times 1 over s squared minus, oh, sorry, in this case, yeah, that should be, that should be negative, right? B should be negative, guys. B should minus 6.25 times 10 to negative 11 BL. I'm about to rerun my numbers in a second. BL over times 1 over 0.5 S plus 100,000. Rerun my numbers real quick. Yeah, it just flips the signs. So D is actually positive. And E is still negative. Right, so just flip the sign on D. Stop it. We're good. C is 0, so we're just going to leave it out, right? Plus ds plus E, right, which is plus 6.25 times 10 to the negative 11 BL times S plus, in this case, we put it as minus BL over 80K all over S squared plus 2 squared. So great, 3 of those things where we can two of those things we can work with, right? So you guys copy that down. I'm going to rewrite that on the next slide in a way that's a little bit better for legibility purposes.
Dr. D,
Yes.
for the B section of the equation, should it be multiplied by 1 over S instead of the 1 over 0.5 S plus 100,000? Because isn't that associated with C?
Yeah, you're right. Yeah, I messed that one up.
Okay.
Sorry. Yeah, you're right. Should be 1 over S. Here, so let's go back for a second. Here, just looking at that. Yeah, so this guy, thanks for bringing that up, Scott. That was good catch. Not bad. The C part is the one that goes away, right? So let's go back here where we wrote it down originally, just to look at it, right? So A, B terms, right? This stays, this one goes away, and this one stays, right? We can do it. I'd like the next slide, please, PowerPoint. But the next slide, not that one. Yes, excellent. Thank you. What's that? I'm just rewriting it so it's on the next slide. 6.25. Okay. So here it is, just written a little bit nicer so that we can see it all on one part, right? So there it is. And that's great. And these first two components, I can take the Laplace transform of and match them directly to the table, right? 1 over S squared is just T, and 1 over S is just a constant, right? So I've got a ramp minus a step plus some sine and cosine, right? This is the part that I'm going to have to take another look at really quickly. Oh, that should be an S. Yes. Thank you, AJ. DL times S. Right. So we're going to take this and we're going to re-look at this, right? And I'm going to say, well, I've got 6.25 times 10 to the minus 4th B times L times S plus negative B L over 80K, 80,000, divided by S squared plus 2 squared. That's a 2. 2 squared. Okay. Well, what's this equal to? Okay. So we go to the Laplace transform table. We go to the Laplace transform table and we say, that kind of looks like sine and cosine together. Also, we know it has to be a sine and cosine because we looked at the roots first. The Laplace transform of sine of omega t is equal to omega over s squared plus omega squared, and the Laplace transform of cosine omega t is equal to s over s squared plus omega squared. Okay, that is what we know from the table. So we are going to say, since I know that, this has to be equal. Well, our omega here is 2, right? Based on the way that I've written this out. So we know that this has to be, and I'm going to use f times 2 over s squared plus 2 squared plus g times s over s squared plus 2 squared. Okay. So now that I know the coefficients for the combined term, I can take the partial fraction expansion of this one and do it again. And the nice thing here, right, is if I multiply this by s plus 2 squared, all the denominators go away. And you can already see what's going to happen here, right? Hopefully. There's only one s term, right? There's only one s term. G has to be equal to this, right? And f is going to be equal to half of this, right? But let's do the math anyway. Well, let's do the math anyway. Don't just believe me. All right, so we looked those up. We found them. We made it look like that. I'll get my s to the 1 terms, which tells me 6.25 times 10 to the minus 4b times L is equal to G. Excuse me. Thank you. I'm awake now. It's better than coffee. S to the 0. Okay, well, I've got negative BL over 80,000 is equal to 2 times F. So F has to be equal to negative BL divided by 460K. Right? So we got G and F, and now we've got everything. We can throw this into our Laplace transform, inverse Laplace transform, right? And by that, I mean we're going to go to the table, we're going to look it up. I'm going to make sure I have another slide here. Grossly underestimated my slide usage. Okay, so we've got this. So now we take this, right? We plug, you know, we plug this into here. We plug this into here, and we take this whole expression and we substitute it in for what's in the red box. Okay. So let's do that on the next slide. Then we're done, basically. And so that was a lot of legwork. Oh, no, thank you. So what do we have? We had x of s was equal to BL over 80,000 times 1 over s squared minus 6.25 times 10 to the negative 11 b times L 1 over s plus, where do we at? Go back. Negative BL over 160K times 2 over s squared plus 2 squared plus 6.25. That's the negative 11th, not the negative 4th. Why do I have to the negative 4th? What is going on? Because I can't read my writing. That's what's going on. 6.25 times 10 to the negative 11 plus 6.25 times 10 to the negative 11 b times L times s over s squared plus 2 squared. Yes. No, sorry. I apologize. It ran together on one time, and then I kept writing to the it's to the 11th, negative 11. 10 to the negative 11, right? Okay, great. We're going to take the Laplace inverse of all of our terms, right? Where does that come from? Comes from the table, right? Because all of these match up in some way. So I'll end up with x of t, right? Because the Laplace inverse of x of s is x of t. I can pull my constant out. The Laplace transform that I got, the inverse Laplace transform of 1 over s squared is t. And the Laplace transform of 1 over s is just 1, right? Or e to the 0, 1. The Laplace transform of 2 over s squared plus 2 squared is sine of 2t. And the Laplace transform of s over s squared plus 2 squared is cosine. Remember, the name of the game is finding exact matches in the table. Right? If you can't find an exact match, we have to do partial fraction expansion. That is what it is. We've got time for another quick one. This time legitimate. Like that's a long one, right? That's a long one. The higher the order, the longer it's going to take you, the more complex the algebra is going to be. If you can run through this one reliably on your own, you are good. You're doing all the things, right? This is a standard Laplace or a standard transfer function method problem, right? If we're doing the Laplace transform method instead, right? Then remember, then you have to incorporate your initial conditions, right? So just make sure you're doing it from the derivative property definition. Right? I will post all my solutions to SoundCloud for all of these through the week, so you guys will have it, right? Because we're obviously not going to get through all of them. I do have one more that I would really like to do. And what you talking about there? No, because the way that sine looks in the table, the Laplace transform of sine of omega t is omega over s squared plus omega squared. And the Laplace transform of cosine of omega t is s over s squared plus omega squared. Yeah. Now, if you had something that was like, if it was like 8 on the top, right? You need to pull a 4 out to make it the right form, right? Okay. We'll come back to the intermission video later if we have time. Does anybody have any questions? So many questions, right? Here's the answer. There are office hours tomorrow from 3 to 5. If you need me at a different time, shoot me a message on Discord or in LoudCloud, and I'll see if I can make it work, all right? Okay. This is the one. All right. Yeah, I'll post them today. Well, probably tomorrow morning because it all depends on how my afternoon class goes. So many pages. Okay. So this one looks familiar too, right? This was an exam 1 question. Matt Sweeney, it says on my sheet that you're the one that is going to lead us from the darkness into the light on this problem. Is it correct? Is that a correct statement on my sheet or no?
Yeah, I was assigned for this one, but I didn't end up completing it.
Fantastic. Okay. Did you do at least a free body diagram? Did you do anything on it?
No.
No. Okay. All right. Rip. All right. So how do we do this, right? Well, the same way that we do all of them, right? So what is the problem statement actually say for us, right? To do. Let me pull that up. Because there's more to it than this, right? But it says use the transfer function method, right? So this is another transfer function method problem. There's no initial conditions. So you know what? In order to prep us maybe a little bit more for the initial conditions, right? I'm going to do this with the properties a long way. So you guys will see what that looks like, right? So what I'm going to do is I'm going to not go through making the entire model right now, okay? For 2 reasons. 1, we've gone through this in class. 2, I'm going to post the complete solution to it after class today. And 3, we don't have enough time, right? So I want to make sure you guys are understanding how to do the newer stuff, right? The stuff that's definitely going to be on the exam. Okay. So if we start from the model, so how would we do the model if we wanted to do the model, right? Well, this one's interesting, right? Because we've got a motor that's controlling our pinion, which moves our rack. And we specifically want using the transfer function method, we want to determine the displacement of the rack, right? But let's for a second say, we're using the transfer function method. So, right, that means all ICs equals 0, right? It means all ICs equals. So, in this case, how would we make the model? Right, how would we make it? We would go all the way through, right? We'd write down our truths, just like we did the last problem, right? You write down your truths, you solve for your circuit model. You write down your truths, you solve for the rack and pinion model. Then you're gonna have to put them together, right? So what will we get out? If we did our model, we should get something that looks like this. J over R plus M R times S squared plus B R S plus K R whole thing times X of S is equal to K M I L of S. All I did was I took the Laplace transform of my equation, right? That's what I did. So I got my model, I take the Laplace transform of it, I group my like terms. But I want to know how we transmit from E in all the way to X of S, right? So I want to know. So how do we do that? Well, remember, we also have our model here, right? Our electric model, which tells us this. Tells us this. Right? We go back and we find the circuit model, we find something like this. And we can take the Laplace transform of this, right? Because this is in the time domain. There's 2 ways that we can tell it's in the time domain. It mostly has lowercase variables, but also you see dots, right? And you don't see dots in Laplace domain, only in the time domain. So let's take the Laplace transform of this, right? And since we're going to pretend we're going to do this all the way out, right? Well, that means that I'm going to have L times, that's my Laplace transform going down. We're going to have L times S times LI, or IL of S, minus I of 0. Right, so that's a first order derivative. Remember, the derivative property tells me this. It's also in our master sheets in the general form, right? So if you have a first derivative, you make the n's equal to 1. Yeah. Plus r times IL of S equal to E in of S minus KB times S, X of S minus X of 0. Well, in our case, right, all of our initial conditions are 0. All of our initial conditions are 0. We get rid of that. And we end up being left with L S plus R laser times IL of S is equal to En of S minus KB S X of S. And I have to get rid of this IL. Right? Because I want everything in terms of X and En. That's all that I want. All that I want. And so 1 and 2. Right? Equation 1 is that first one I wrote. Equation 2 is the second. So what now? What now? Well, now I'm going to solve this equation for I sub L, right? Because I want to eliminate the currents. And the current, IL of S, is just equal to En of S minus KBS X of S over LS plus R, right? That's just divide out by LS plus R and you get I of L. And you can take this whole guy, and we're going to take this and we're going to throw it up in here. Right. Take this, throw it up there. We'll get a big, nasty looking equation, right? Which is we're going to get a big nasty equation when we substitute those things together. I know I'm frozen on the internet. This thing is going to do it again. Yep. Right. Look at that. That's actually not that bad compared to the last one we just did. That's actually very nice. Like a comforting. I wouldn't go that far, right? So what do we do now? Well, now we're going to multiply through by ls plus r, right? Why do we want to do that? Because I want all of my x sub s's on one side and all of my ENs on the other, right? So I need to multiply through by ls plus r so that I can then add kbs x of s to the rest of my x of s terms, right? So let's do that, right? We'll end up with L J over R plus, well, you know what, we're gonna do it this way. J over R plus M R, whole thing times L times S cubed, right? Because I'm multiplying the LS first. So basically, right, I'm going to take the LS, do every term by LS, take the R, do every term by R. That's what I'm going to do. Plus LBRS squared plus KLRS plus R times J over R plus MRS squared plus BR squared S plus KR squared. This whole thing, right? This is my X of S term. So everything there gets multiplied by X of S and the entire thing. And so I'll put it over here so we can actually see it. That's times X of S. And this entire bad boy is just equal to KM E N minus K B S X of S. Now I'm just going to add that KBS X of S. So add this KBS X of S over, right? Add it over to the other side. So Km En is equal to L times J over R plus MR S cubed plus LB R plus J plus MR squared times S squared. So I've done some algebra. I'm doing some algebra as I go. Right? Okay. So I've got this. I want the transfer function. Transfer function is my output divided by my input. Right? So if I divide out by this long characteristic equation here, right? I get this as my transfer function. And when I plug in the numbers, right, this actually is not so gross anymore, right? Because I have values for all of these things. So Dr. D, why didn't you just put the values in to begin with, right? Because what if your values change? What if your values change? What if all of a sudden your company says, you know what, I don't want to use an L of 2, I want to use an L of 20. What if I can't get that spring anymore and I need to use a stronger or less stiff spring, right? I have to make design changes. If I have to make design changes, having this all written out in terms of the numbers doesn't help me. Because guess what? Your company doesn't want to wait for you to redo your entire analysis because you have to redo the entire thing instead of just being able to plug things in right at the end and then do the analysis. Right? So yes, it takes more work up front, but now I have a model that is ready to go for any conditions, right? So we're gonna plug our numbers in. So let's plug our numbers in. So if I plug everything in, right, and I realize I'm paused on the internet, right, so I'm trying to let you guys catch up with the writing. I'll get 20 divided by 51.2 s squared s cubed plus 158 s squared. So there's a lot of algebra. There's a lot of algebra involved in getting these set up. So what happens? I get everything ready, plug in all of our numbers, we get something that looks like this. And this looks manageable, right? That's a third order system. Yeah, that's a third order system. Okay. So what are the roots of my characteristic equation here, right? Well, if I solve for the roots here, if I solve for the roots, I'll get negative 0.0724, negative 0.7424, and negative 2.271. And when we see that, right, we jump for joy, we scream hallelujah, right, because we've got three real distinct roots. And that is the easiest partial fraction that we're going to come across, right? But there's one thing that we haven't done yet, right? Because I want x of s. And if I'm going to get the response of the system, I need to have this whole thing, right? And I'm going to write this in terms of my roots. Right? So I'm just factored my all I've done is factored my denominator. We were told at the beginning that En of S or En of T, right, was 12 volts. And I need to multiply this whole thing by En of S. So I have to take the Laplace transform, right? What's the Laplace transform of a constant? What's that, Adrian?
The constant.
No. The Laplace transform of the constant. Right? Is a constant just a step function? What's the Laplace transform for a step function? Not zero. Yeah, 1 over S. So this is just 12 over S. So I got to put 12 over S into this. And look what happens. I've got 4 distinct roots. I've got 0 and all the ones that I listed above there, right? So I can do a partial fraction for this. And if I do partial fraction decomposition here, right, I'll get this 20 times 12, right? Well, I'll write it over here. This is 20 times 12, but 20 times 12 is just 240, right? 240 times 12 is 240. This is going to be equal to A over S plus B over S plus 0.0724 plus C over S plus 0.7424 plus D over S plus 2.271. I'm going to run straight through, right? Multiply through on both sides, right? By this whole, I'm going to use the term, I'm going to say that all of this is equal to CD for common denominator, right? You know what, why don't we make it less confusing and we'll just call it den. I'm going to multiply everything by den, right? I don't feel like rewriting that giant thing. So I'm calling that entire denominator DEN, and I'm multiplying everything by DEN. Okay, we've done this a couple of times. Right? We've done this a couple of times. So what do I end up with, right? Well, I'll end up with 240, right? Because 20 times 12 is 240. The denominators cancel from the top equation. This has to equal what? Well, this has to equal 51.2 times A S cubed plus 158 AS squared plus 97.5 AS plus 6.25 A. Right? Okay. So how did I get that? This is A over S times S plus times S plus 0.0724. Right? So these S's cancel, right? And I'm left with just the original equation, right? I'm just left with the original characteristic equation if I get rid of that S. And so I'm just left with the original function, right? For B, I have to get rid of this term, right? Because these two terms will cancel when I multiply through by the denominator. So it's going to be B times, so distribute through B times S plus 0.742 plus times S plus 2.271. Yeah, it's, look, not joking, right? This is like, I know these take a while, right? You're not going to see a million problems on the test, right? You're not. Right, but we've got to do the algebra. So I'm going to write it out. 240 is equal to 51. Don't do it. Let's do it over here. 240 is equal to 51.2 AS cubed plus 158 AS squared plus 97.5 AS plus 6.25 A plus BS cubed is 3.01 BS squared plus 1.69 BS plus CS cubed plus 2.34 CS squared plus 0.1644 CS plus DS cubed plus 0.8148 DS squared plus 0.0537 DS. Okay. Our largest S term is S to the third. So we're going to gather all the coefficients. On the left-hand side, these are 0 until we get to the S to the 0 term, right? On the right-hand side, we have 51.2 A plus B plus C plus D. For S squared, we get 158A plus 3.01 B plus 2.34 C plus 0.8148 D. S to the 1, we get 97.5 A plus 1.69 B plus 0.1644 C plus 0.0537 D. And for the last one, we only have this. You've got to solve them. Negative 2250.5. And this is what we end up with. We're going to take those, and we're going to plug them back in to our x of s equation. I'm going to add a slot. So take that. I've got x of s was equal to a over s plus b over s plus 0.0724 plus c over s plus 0.7424 plus d over s plus 2.271. I can inverse Laplace this based off of my table. Inverse Laplace transform of x of s is x of t. 1 over s is just the constant, 38.4. 1 over s plus a is e to the negative at. And these are all going to be e to the negative at. I'll scan and post those today or tomorrow morning. If you can do a third order system, right, out by hand, then you are good, right? Keys, understanding the root responses, right? Take what we know from the root and make sure that you're getting a solution that is in the form that you would expect it to be, right? Yes.
Dr. D,
Yeah.
real quick, when we multiplied the denominator through, how did we get like such high values like 51.2 and 158 for like the AS to the third? And
Good question. All right. So how indeed? So let me do it here, right? So for AS, right, we've got A over S times S times S plus 0.0724 times S plus 0.7424 times S plus 2.271, right? So we're going to cancel those S's, and we're left with this, right? And this came from the original equation.
Gotcha. Okay.
So all I did was I basically expand that trinomial, right?
Okay. Thank you.
Algebra, man. Lots of algebra. We didn't really do any calculus or anything here. We're just doing algebra. Any other question? Take a look at the homeworks. Take a look at these problems that I'm going to post. Any other examples that we've done in class, right? If you can understand how to do the more complicated ones, right, then you'll be fine with the easier ones. Yeah. I hear chuckling, presumably because what's the difference between the hard ones and what Dr. D thinks are the easy ones? I'm guessing. This one's easier than the first one we did. This is not like a super easy one would be like a second order system that has like a step in, right? Because then you know you're at max, you're looking for three roots, right? That's on the easy one. Some of it's dictated by what your roots end up being, right? If you have, an overdamped system, that's going to look a little bit different. But you guys, we've seen problems where we've used damped sine and cosine, right? We've seen problems where we use regular sine and cosine, right? Always look at the roots, determine what kind of responses the roots are telling you you're going to get, right? And then look at the Laplace transform for those types of roots and understand that that's where you need to try to get to. Okay, that's where we need to try to get to. It feels like you're trying to force the solution to be looking a certain way, right? That's how it feels. But that's not what it is. What it is that you understand enough of the mathematics behind what is going on that you know you can guide to where you're supposed to be. Essentially. Official office hours from 3 to 5 tomorrow. If you have free time during the day and you were wondering if I have free time during the day, you can message me with Discord or with private message in LoudCloud or send me an email, right? And we can try to set something up earlier in the day too if it turns out that I'm around. Okay. Anything else? All right, just one final announcement, I guess, before we turn it over to the end of class stuff. After Thanksgiving, um, I haven't been real strict with it up until now, but after Thanksgiving, if you're watching only on Zoom, right, and you don't have your camera on, I'm gonna assume you're not here and I'm just gonna kick you from class. Okay? Now, I understand that sometimes people have internet issues, right? And I'm not trying to be a jerk about it. So if that's the case, let me know and we can do a workaround. But if you're just logging in to get your participation points because you're Zoom only and that's what might be happening, I'm just don't bother. Right. Okay. Cool. So now that I have apparently destroyed everyone, how are we feeling? How are we feeling about class? Yeah, I'm imagining it's gonna be lower half today. I'm imagining. Yeah. So the big things, right? Remember, if you're asked to do something a specific way, do it that way, right? If you're asked to use the transfer function method, you better be doing the transfer function method. If you're asked to do impedance, you better use impedance. Okay. If you're on the bottom half, you gotta come to office hours. I cannot help you if you don't come see me and talk about what is going on. Okay. I want you guys to do well. I want you guys to succeed, but I don't read minds. And if you're having issues, we need to talk. So come to office hours.
Just to confirm, you're going to post these work problems either tomorrow or Saturday, you said?
I will post them at the latest tomorrow morning, Carl. It all depends on what time I get back to my office today. So either
Okay.
tonight or tomorrow morning, you'll get them.
Okay.
Well, I suppose that'd be tomorrow afternoon for you, but you get the point.
Yeah, sorry. I actually, yeah, never mind. Okay, thank you.
Yeah, no problem.
Dr. D,
Yes.
my Zoom camera often goes out and I only have 50-50 chance of knowing when it does when I open Zoom.
Yep. So, Julius, that's fine. That's one of those things that's outside of your control, and I know you're here, so that's fine.
Okay, thank
I just
you.
want to make sure that people are actually in class and participating. That's the whole thing. So.
Okay, thank you.
Sure. Sure. Yep.
Thanks, Dr. D.
No problem. Take it easy, Doctor.
You too. Bye.
Yeah, you can always use the chat to your advantage, right? Chat for the win. Sure.